A pre-stressed concrete beam of inverted T-section has the dimensions of rib 300 by 900 mm and flange 300 by 600 mm. The beam is simply supported over a span of 15 meter. The beam is post-tensioned with 3 Fresnel cables, each contained 12 wires of 7 mm dia, placed at 150 mm from the soffit at the midspan. If the initial pre-stress is 1 kilonewton per mm square, calculate the maximum UDL that it can carry if maximum compressive stress in concrete is limited to 15 MPa and tensile stress is limited to 1 MPa. Assume 15% loss of pre-stress. By looking into the problem statement, a sketch has to be drawn very clearly. So the rib dimension, that is web dimension, is specified as 300, width, depth is 900 mm, and flange 300 by 600 mm. So here, since 600 mm is longer, and we shall consider that as the width of the flange, 300 mm we shall consider it as thickness. So inverted T section, as all of us know, we need to draw the sketch in a direction opposite to that of the T section. So here we shall draw the sketch. So it is an inverted T section. So it is having width of 300 rib or web, and flange is having 600 mm width and 300 mm depth, and it is also carries 3 number of the Fresnel cables. So cable 1, cable 2, cable 3. So this each cable is containing 12 number of the wires. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So likewise it is having totally 12 number of the wires which makes a single cable. The die of each wire is 7 mm. And here the right hand side picture, we need to compute what is the load it can carry. That is why here WQ is mentioned with the question mark. And next let us proceed with the calculation. Cross sectional of the area of cable. So here there are totally 3 number of the cables. So therefore 3 cables, and each cable contains 12 number of the wires of dia 7 mm, and that is how we need to calculate what is the total area of the cable. And pre-stressing force. So the conventional expression sigma is equal to P by A. So with this expression we can rearrange it and can find out what is called as pre-stressing force here, and after substitution it is obtained as 1.385 10 power 6 Newton, and cross sectional area of the beam. So it is having 2 number of the rectangular section. It is having 2 number of the rectangular section. One is rib portion, one is flange portion. So area of the rectangle, that is B into D, 300 into 900 plus 600 into 300. That is how the area is computed here. The total area works out to be 450 into 10 power 3 millimeter square. And now as we are aware it is a flanged section, we need to locate the neutral axis. The conventional method of locating the neutral axis, that is finding out the centroid, goes with the traditional method, that is y bar, the conventional expression a1 y1 plus a2 y2 divided by summation of ay. This is the conventional expression to find out what is the centroid. And now after applying the equation we need to find out y. Okay, let us consider the very first thing is rib portion. Let us consider the rib portion here. And 300 into 900 is nothing but this rib portion area, 300 into 900, and we are trying to find out the neutral axis with respect to the bottom fiber. So this is the bottom fiber. So the area of the rib portion is 300 to 900, and next we shall take this, whatever the purple point I have to consider, let that be the centroid of this rib portion. From here to here the distance is very much necessary. So how much is that distance? So we can split it. From here to here it is 300, and from here to here you need to find out the centroid of a rectangle section. It is b by 2 comma d by 2. The total depth is 900. 900 divided by 2 is 450. 450 plus 300, the total distance is 750, and that is how here 750 is written. And next we shall come back to the web portion. So coming to the web portion, the area of the flange portion, coming to the flange portion, the area of this flange is 300 by 600, and here we are again trying to find out with respect to the bottom fiber. And let me locate the centroid with the red color, and this is the centroid of this flange portion, and from here to here the distance is d by 2. D is nothing but 300 by 2, and 300 by 2 is nothing but here 150. That is how it is written here as 150. Soon after locating y bar, the y bar final value is obtained with respect to the bottommost fiber. It is 510 value. Let us locate the same in the sketch. Okay, in the sketch, so this 510 is located with respect to bottommost fiber. The total depth is 900 plus 300, that is 900 plus 300, it is 1200. 1200 minus 510 is nothing but 690 with respect to the top fiber, which is been indicated here. And next step is to determine what is the moment of inertia with respect to the centroidal axis. Determining the moment of inertia is very important. Determining the moment of inertia is very important. So let us try to locate the moment of inertia. Let's understand it in the simple and easy way. Okay, moment of inertia, here we are applying the parallel axis theorem. As all of us knows what is parallel axis theorem, Ixx is equal to Igx plus A into y bar square plus A into y bar square. So we are applying the parallel axis theorem in order to find out what is the moment of inertia through the centroidal axis. And now let us begin with that. So here Igx formula, the moment of inertia of the rectangle section is BD cube by 12, is BD cube by 12. B is 300, depth is 900. Now we are trying to actually compute it for web portion, and BD cube by 12 is the formula for the moment of inertia of a rectangle section, plus according to the principle of parallel axis theorem, it is A. A is nothing but the area of this rib portion or the web portion, 300 into 900, plus h square or y bar square is nothing but it is the distance between the centroidal axis of the flanged section to the centroidal axis of the rib portion. And let me locate, it has been already shown that this is the centroidal axis of the flanged section. However, the centroidal axis of the rib portion is located here. Let us say, for example, y bar is nothing but the distance between the centroidal axis and the centroid of the rib, and that is how this is 690. We know already this distance 690 minus the centroid of the rectangle, we know that it is d by 2. So the total portion is that the total depth of the rib is 900 divided by 2 is 450, and this is 450, and after calculating 690 minus 450 comes out to be so much, and that is how it is written here. And in the similar fashion it has been computed even for the flange portion as well. So firstly we have taken the moment of inertia of the flanged portion. Moment of inertia of the rectangle section is again BD cube by 12. B is 600, D is 300 cube by 12 plus area 300 into 600 plus, so this side it is 510, and the distance between the centroid, this is the centroid of the flanged portion, the distance between the centroid of the flange portion to the centroidal axis of the flanged section, that is 510 minus of 150. 150 is nothing but this 300 by 2. I hope it is clear to all of you. And next, that is how we compute moment of inertia, that is obtained as 5.85 into 10 power 10. And next step is to find out what is the section modulus. Section modulus, as I have told you, if it is unsymmetrical section or built-in section, we need to apply the fundamentals in order to determine the section modulus, and there is no direct formula like the rectangle section or any other simple planar figures. The general definition of the section modulus is defined with respect to the depth of the neutral axis and the moment of inertia, that is I by y. It is as shown in the calculation part. Okay, so this is the calculation part of the section modulus. So it is simple calculation. Here we have to take y top. If you are calculating section modulus at the top, it is, you need to consider the centroid with respect to top fiber. If it is computed with respect to bottom fiber, centroid with respect to bottom fiber. However, the moment of inertia at the centroidal axis remains same. Soon after calculating section modulus moment of inertia, we need to determine the eccentricity of the cable. In the problem statement, it is given that the cables have been located at a distance of 150 mm from the bottom, 150 mm from the bottom. And then what is the eccentricity? The cables are located at 150 mm. So this is the bottom fiber. So the distance between these two is 150. So from here, the center of the cable to bottom fiber, it is 150. But we need to find out the eccentricity always with respect to the centroidal axis. This is nothing but the E distance. This E is calculated as 510 that E is calculated as 510. E is calculated as 510 minus 150. So that is how it is being computed, which has been shown here, 360. And next, let us go to the calculation of the dead load of the beam. As usual, dead load of the beam is calculated as area into density. After substituting everything, 10.8 kilonewton meter per meter will be the outcome. And dead load bending moment, we are trying to calculate it at the central span. And the most important condition here is that the given permissible stress at the top, it is 15 MPa. At the top, the beam is subjected to the compression. Bottom, it experiences the tension, which means F superior has to be equated to 15 MPa. And here the major thing is that we need to account for the losses. In the data, it is given that loss is 15%. So out of 100%, the loss is 15%. What is the remaining? It is 85%. That we are calculating in terms of ratio, and that is how we got it as 0.85. That has to be taken into account only for the pre-stressing phase. So here, that is, see here in the first two part of the expression, see here pre-stressing, see this losses occurs only during the pre-stressing phase, that is during the transfer phase. That is only during the transfer phase the losses has to be accounted here, and that is why it is been multiplied here. And here there is no multiplication, because when it is subjected to the loading conditions or the service conditions, losses is accounted in the later phases. So in the preliminary phases, the losses during the stage of pre-stressing has to be considered for the direct stress and stresses developed due to the bending. After substituting everything, Finally, we get the bending moment due to the loading, live loading as 1169. The second condition is that permissible stress, tensile stress is limited to 1 MPa. Here, the sign convention for the tension is negative. So that is why it is very much necessary that the tension sign convention is made accountable here. That is -1 has to be considered. This is -1, and here in addition to that losses also has to be taken into the account, and finally F inferior has to be made equivalent to -1 MPa. So as we seen in the sketch here, the compression is expected at the top, therefore a superior expression is considered here. See, since compression is expected at the topmost fiber, F superior is equated to 15 MPa, and whereas in the case of tension, tension is acting or expected at the bottom fiber, that is tension is made equivalent to the F inferior, and that is why F inferior is made equal to -1 MPa. So after this, certain calculations need to be done. That is, after complete calculations, MQ value, one more case, 534. So in the design phase or finding out the loading criteria, it is necessary to consider the least among the two cases. So the least value among two cases is 534, and again it need to be equated into WL square by it, the general bending moment equation. So after all that simple calculations, it is found to be 19 kilonewton per meter.